Good morning, students. Now we are going to design of purlin, and for that, in this presentation, I am going to cover the load calculations, that is your dead load, live load, and wind load. And the problem is, a fleet roof truss is supposed to be constructed at Chennai. The pitch of the roof is 1 by 4 for a span of 12 meters. The trusses are spaced at 4 meters center to center. The roof is covered using a GI sheeting, and the height of the roof above the ground level is 12 meters. The configuration of the truss is given. If not, you have to arrive out using your type of truss which is given in the problem. Here I have given the both. And design of channel purlin for its worst load combinations. That is, what is the combination? You have to find out which is going to create a worst effect, and for that forces you have to design the purlin. And assuming the self weight of GI sheet is 0.133 kilonewton per meter square, if the GI sheeting or the self weight of the roof material is not given, you have to refer IS 875 part 1 for the loadings. The structure is located in the outskirts of the city with less number of obstructions. So this is going to help you in finding out the wind load. Now, the problem is pitch of the truss, that is 1 by 4 of span which is given. So 1 by 4 of the span of the truss is 12 meters, which is equal to 3 meters. The inclined length of the top chord you have to find out, because then only you can able to limit whether you can place the purlins exactly at the nodal points or at the panel length. So x is equal to, using the same Pythagoras theorem, root of 6 square plus 3 square. 6 is nothing but half of your span, which is equal to 6.71 meters. Now, the configuration is given in the problem. In this configuration, if you see, there are 4 panels in the truss. So 4 panels, you have to divide the inclined length by 4, which is equal to 1.67 meters, which is less than your 1.7 meters of a GI sheeting. Why it is in case of a GI sheeting is, GI sheeting, the spacing of purlin, because here you can place one purlin, here, 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 as well as here. So the purlin locations you can place exactly at the nodal points. Why I am checking with 1.7 meters? This is the maximum spacing of purlins, which depends on the length of the sheeting. GI sheet has a maximum length of 2 meters available. So 150 mm on either side is for nailing the nails or screws in the purlins. So, or in other words, it is the bearing length. If you deduct 0.3 meters, that is 0.15 on either side. So 0.15 into 2 is 0.3. So 2 minus 0.3 is going to be 1.7 meters. This is going to be the exact center to center distance of the purlins. So you can place the purlins exactly at 1.68 meters, which is not going to affect the fixing of the sheeting. Next, what is the angle of inclination of the truss? You have to find out. Angle of inclination is equal to tan inverse of 3 by 6, which is equal to 26.57 degrees. Now, what is this? In the problem, they have given the spacing of the truss as 4 meters. So, this is your spacing of truss. What is the other input? Truss to truss only I am going to place the purlins. So the span of the purlin is also going to be the 4 meters, and I am going to place the purlins exactly at the nodal points. Now, load calculations. Dead load. As per IS 875 part 1, self height of GI sheet is equal to 0.133 kilonewton per meter square. If you refer part 1, in that the sheeting self weight is given either in kilonewton per meter squared or in kg per meter squared. Self weight of the purlin we assume as 0.050 kilonewton per meter square, because we are going to design the purlin now. If you are going to design the truss, you have to assume the self weight of truss, which is not going to be equal to 0.05, it is going to be a different value. Then additional services and fixtures. This is for the additional services which we are going to connect to the purlins. For example, this electrical pipelines or services, you may fix it out. For that, fixtures. Fixtures means your nailing or screws which is going to use for the fixing of the sheeting. This is equal to 0.2 kilonewton per meter square. So if you sum it up, it is equal to 0.383 kilonewton per meter square. This is the area load. You have to convert this area load into a concentrated load. How I am going to convert it? I am going to multiply with the area. So what is the effective area? Effective area is nothing but spacing of the purlin into length of purlin. If you see, yes, this effective area is half of the panel length on the either side. That is going to be the width. Here it is 1.67 equally. So 1.67 by 2 this side, 1.67 by 2 this side. This is going to be equal to your spacing of purlins and the span. So this is going to be your, what to say, effective area. So effective area is spacing of purlin into length of purlin. So dead load is equal to, this is your 0.383 kilonewton per meter square into spacing of purlin is 1.67 and length of the purlin is, or span of purlin is 4 meters. So it is going to be, dead load is going to be 2.56 kilonewton. You either use 1.68, that is also well and good, fine. Now live load. Live load, you have to refer IS 875 part 2. Considering the angle of inclination and the accessibility of the roof. Now, it is only for maintenance because the angle of inclination is around 26.57 degrees and we assume that the roof is going to be accessed only for the fixing of sheeting or maintenance of sheeting or repair of the sheetings like that. So, the live load or the imposed load as per the code is 0.75 kilonewton per meter square when theta is equal to or lesser than 10 degree of slope or angle of inclination. So when your theta is 26.57, then there is a formula or you have to reduce the live load acting on the roof truss. So how I am going to reduce it? For every degree increase above 10 degrees, I have to subtract 0.02 kilonewton per meter square or reduce the live load by 0.02 kilonewton per meter square for every degree increase. So how much degree I have, that is for my trusses, it is around 26.57 minus 10, it is 16.57 degrees is increase. So for 1 degree it is 0.02. For this difference, I have to multiply with 0.02. This I have to deduct from the actual loading of 0.75 kilonewton per meter square, which is equal to 0.419 kilonewton per meter square, which is going to be the reduced live load acting on the structure. So live load is equal to 0.419 into 1.67 into 4, which is equal to 2.8 kilonewton. Now, wind load. What are the inputs we need? Actually, it is given also in the problem. The location of the structure, that is Chennai, and the height of the structure above ground level, it is 12 meters. As per IS 875 part 3 annexure A, wind speed for Chennai is 50 meter per second. So, design wind speed you have to calculate, that is Vz. The various effects are K1, K2, K3, K4 factors. K1 is your risk level, K2 is your terrain roughness and height of the structure, K3 is your topography, and K4 is your cyclonic importance factor. Now, we know what is your VB value, that is your basic wind speed, which is 50 meter per second. Now, what is K1? K1 is your risk coefficient. When you refer table number 1, the class of the structure is not given in the problem. So it means that all general buildings, class means you have a that is temporary sheds, that is what is the lifetime of the structure also you have to consider. So based on that, for all general buildings, it is going to be for this speed, your K1 is going to be 1. Then K2 is your terrain roughness and height of the factor. The structure is located in the outskirts of the city, which is given with less number of obstructions. So it comes around category 1, and the height of the structure is around 12 meters. So referring to table 2, if you have this, if you see it is around 10 meters, your K2 factor is 1.05. For 15 meters, it is 1.09, but your height of the structure is 12 meters. So you have to calculate or interpolate and find out what is the value of K2. So K2 is equal to 1.066. Then K3 is your topography factor. If you refer the class, it comes around 1. Then K4 is your importance factor for the cyclonic region. So as per the clause 6.3.4, the structure is